Hello everyone. As Uri said, I'm Benjamin Kempinski, I'm a data scientist at Argmax. And today we'll talk about evaluation of recommendation system and offline metrics. And do need to start in saying that in contrast to the previous two lectures, I dealt more with the more advanced topics like deep learning and multi-armed bandits. This one will go more to the basics. So let's start at the very basics. Why do we need good recommendation systems? Why do we need to differentiate between good and bad recommendations? And why do we need to know, or can we know, what a good or bad recommendation is? So, this would be an example for a very bad recommendation. It is very important for us to know to differentiate between good and bad recommendations, because I sincerely hope that no child or parent would ever have to act on this recommendation. And for those of you who do, my sincere apologies. So we need to ask ourselves, so if you want to know what a good recommendation system is, we need to first understand what recommendation systems are. Recommendation systems usually go in two branches. One will be the complementary branch and one in the similarity branch. The complementary branch deals with items that are complementary to the items that you are viewing or interacting with. Items that are in a very narrow field of domain that you are interacting with, and so usually depend more on the item description that you are seeing. The similarity branch deals not only with the items in such a narrow field, but also explore and go to different branches and go and try to find new items in order to enrich your experiments. So for example, if I would buy a camera at Amazon, I'm expecting also to get recommendation for a memory card or for a case in order to hold the camera, all relating to the said camera that I am buying. However, if I'm going to the entertainment business, there is no such thing as a book that I need to read in order to understand another book, unless you're in academia, and that's a very narrow niche. However, if you're listening to some music, you want to find music that is similar to that music. So if I'm listening to Beethoven, I'm expecting to hear other romantic musicians such as Chopin, Brahms, Grieg, and maybe explore a little bit and go to the classical like Handel. But this lecture will deal more in the similarity branch. In the similarity branch, all recommendation systems have the same architecture, which looks like this. I am interacting with one specific item. This item can be translated into some vector of embeddings or features. This vector is entered into our search engine, which looks across the entire catalog of items that we have, and tries to find us the most similar vectors in our catalog. Now comes the question, how do I know that the items that I received from the catalog are relevant or good to us? If I bought a Mickey Mouse sticker, I might want to buy a Mickey Mouse t-shirt, but I won't necessarily need to buy a Mickey Mouse toaster, even if both of them have a Mickey Mouse. So I need to evaluate them better. How do we evaluate them? There are two ways, again, to evaluate things. One on the online branch and one on the offline branch. In the online branch, the most common thing is A/B testing. A/B testing, for those of you who don't know, is of course that we're taking a subsample of the users that we have, and we present to them a new thing, either a new model or a new recommendation or a new data set, whatever we want. And this subsample of the entire user base that we are seeing, we record their interactions with the existing item, with the new thing, feature, model, whatever that we are presenting to them. And we record and see the differences. After a time that we measure that experiment is over, we can say and evaluate how much this new model is improved in contrast to the first model. Another option is, of course, going to the more expensive option, and that is taking the family and friends options, which is we're taking users that we pay them specific more money, and then they will give us detailed evaluation of the model that we're presenting to them. Both of these, so for example, you can have several testings at the same time, of course, because we want to show model A, B, C, D, E, or A, B, C, D, D, and then model E will be our baseline, which is the model that is currently in production. All of A/B testing, and be it for family and friends or for subgroups, have the small problems that they are costly, either because we are paying the users for more detailed information in their time, or because we have to pay for mostly to some platform that gives us the services of A/B testing. Optimizely, whatever, they have some subscription and it costs money, also it takes time. This time it takes a lot of time to gather all the data that we want to know, and we have to plan the tests in accordingly. We need to know what we're recording, and the recordings are mostly only actions, meaning we have immediate feedback. What do you mean immediate feedback? We cannot record all the information that we want. We only get positive actions, for example, how many clicks or how many buying actions were performed. If I want to know more implicit information, like how was the user experience, how the model improved not only the buying information, but also the level of interaction or how it was according to your taste, I cannot get that much information, and so the A/B testing are limited. Multi-arm bandits were explained in the previous lecture, and they deal in some ways to improve the A/B testing, that we are testing more smartly, a more improved way in the online evaluations. But since they were explained more in the previous lecture, I won't delve too much into it. If we go to the offline bench, we have to ask ourselves first how much, we can see there are several algorithms here, but we have to ask ourselves several questions before that. One of them would be, how do we evaluate, or what do we expect to get from these evaluations? How much we are covering from the catalog? What is the quality of recommendation that we need to get in contrast to what we are currently viewing? How much more do we need to improve our precision or our recall? And how much is important for us, or at all, the ranking or the ordering of the items that we are presenting to the users? What I mean by user coverage? By user coverage, mostly what we do is take several users. We sum all the items that the user is seeing, and we get a rough estimate how much the average user sees from the entire catalog that we have. So, for example, I'm pretty sure that I've never seen more than, not even closely to 1% of the Amazon catalog. However, I'm pretty sure that most of you have seen more than 1% of the Netflix catalog, especially now after the quarantines. Why the reason that we also want to show about the entire catalog and know which user sees from the catalog is the problem of the Pareto principle, or the long tail problem, which is, while most items or most interactions or purchases in retail industry would be in the head of these popularity product functions, where several millions or billions of batteries are sold each day, their worth is very small. Amazon won't get most of its money from that, from these interactions. However, Amazon does get about 40% of its all revenue from the items that the farther they are along the long tail, where the items are more exotic but also more value. If you're not going into retail industry but into entertainment industry, the long tail has the added value of not only having items that are more niche and so perhaps less popular, less on demand, but they're more tailored to you. Users who find that esoteric students movie in Netflix feel that Netflix has more options and is better than any other platform of entertainment movies. So we want to know, now we want to know, now that we know we want to improve which part of the catalog we will see, we want to ask ourselves which algorithm we're going to use in order to evaluate our offline metrics. Let's start with precision at K. Precision at K is a very simple classification problem. You ask yourself, if I'm showing you several items, how many of those items are relevant to you? Relevance to you in this case will be either the item is relevant or not relevant to the item presented to you. And you simply sum the number of relevant items divided by the number of K that you decide of the item that is being shown. So, for example, if I'm showing to you Mickey Mouse and Minnie Mouse, or Minnie Mouse and Mickey Mouse, and you buy Mickey Mouse, or Mickey Mouse is relevant to your purchase, then you can say that the precision at K for precision at 2 is half, because there's one item relevant in these two items that are shown. Of course, the immediate thing that you will ask yourself is, wait, but is the ordering important? In precision at K, this and this would be exactly the same, because there are two items shown, and irrelevant if it's the first item or the second item, both of them, if only one of them is relevant, the same score will be given. We know that most users do find relevance in the ordering, and it does affect how the user buys or how much he buys in the platform that he uses, and so we want to improve the ranking. So if we want to go to ranking, we need to take a different algorithm. Such algorithm perhaps would be mean average precision at K or map at K. Map at K takes the precision at K formula and simply sums it across each item of the recommendation relevance. Meaning, if I'm going to ask what is the map at K at map at 5, the answer would be what is the map at 1, map at 2, map at 3, map at 4, map at 5, sum it all together, and divide it by the number by k, the number of items I want to show. If I want to know what map k is for the entire user base and not for a specific user, I will then divide again that sum by the number of users that I have. So, for example, if for user 1, those 5 items, only 3 of them are relevant, 1, 3, and 4, then mapped 1 would be 1, mapped 3 would be 2 because there are 2 items relevant of at the third position, mapped 4 would be 3 over 4 because there are 3 relevant items at the fourth position. Sum them all up, divide them by 3, we get the we get average precision of user 1. Do the same thing for user 2, who has less better result. We get the average precision for user 2. Sum them up and divide by number of 2, we divide by 2, we get a map of the algorithm for this user base. The next question that you should ask yourself is this: why is it so simple? Most items aren't relevant or not relevant. There is a scoring, there is a ranking, there is some metric that you can decide how much item is the same or not the same, how much a user is enjoying the items, or how much he finds the recommendation relevant. In order to make it binary, I either make a arbitrary distinction saying that above such and such score, I'm saying it's relevant, and below it, it's not. And usually you're using data in that problem. So in order to get info more relevance details or relevant levels, I'm going to go to the different algorithm. It's called discounted cumulative gain, which is DCG. DCG assumes that there are relevance levels, meaning that I no longer a binary problem, but a multi-class problem. The function looks a little different, but it's actually the same. There is a relevance score, meaning which degree of relevance the item is, and it's divided by the log of the location plus 1. DCG also has the relevance for each ranking is different. There is also a normalized DCG, which takes the ideal DCG scoring, meaning what is for a certain recommendation, what would be the ideal ordering of those items. What does it mean? If I'm having this list of items with these scores of relevance, I can get the DCG score for each item according to the ranking and ordering of them in this list, get a DCG score, compare it to the IDCG, which is the ideal ranking, meaning ordered ranking of the items according to relevance, and dividing those two, I will get the normalized DCG. Of course, the closer it is to 1, the more happier I am. But now comes another question. This means that I have to order the ranking of the relevance of items. But a catalog usually is not something that stays static. All the time we'll get more and more items to the catalog. All the time we'll have to reevaluate them. We'll have to decide how much relevance they are. I'll have to reorder what is the most relevant or the less relevant item. And so the ordering and the ranking would be a non-ending task, and it will cost a lot of time and effort from us to maintain such a database. In order to surmount such a problem, we need to attack the problem differently. We need to attack the recommendation as a regression problem, not as a ranking problem. When we attack the recommendation as a regression problem, we are saying two things. If I'm saying that I have some score of the similarity between two items, I can then get the ground truth matrix that says for me how much one item is similar to another item. And then can take a model, ask it how for one item in each feature to find the most similar, to multiply it, find the Gaussian similarity between that item and all other items in my catalog. And then I will get a matrix of similarity between each item and each other item in my catalog. This matrix that I'm getting from the model can be compared to the annotation or the ground truth that I'm getting from people who know the catalog better and can give me an actual assessment of the data, or from people who I can ask to do it for me if there is no ground truth for such subjective items like how much one book is similar to another book. The comparison between those two will give me then the scoring of the model and how good or how improved the model is compared to our previous models. In order to get such annotation that how to get to ground truth, we went to Mechanical Turk and we simply gave them this questionnaire. We give them one song, ask them to play it, and ask them which of these instruments is in that song. Then we ask them to take second song, Again, asking them which of the instruments are in that song, and then asking them what is the ranking similarity. The thing that is most obvious here is the question, what is this? Why do we need to know which instruments are in the songs? It is irrelevant. We only want to know what the score is. So why do we ask them? The answer is simple. We want to verify that they actually listen to the songs. We want to know that they have listened, that they know what they are talking about, and not simply clicking random buttons. Mechanical Turk is a platform of Amazon that allows us to go to the wisdom of the crowds and ask them such questions, in that we are in giving them so many songs and multiplying the answers and collecting the data of all these songs, we can then get the opinion of several hundred people about each song pair. And as we all know, the opinion of one person is an opinion, but the opinion of a lot of people is data. If we take the data of all these songs, we can then get the ground truth, or as close as we can, to such subjective matters as how much one song is similar to another song. Of course, there is in the fact of the cost, but Amazon Mechanical Turk is relatively cheap. I think for each song pairing, it was something like 20 cents.
That's how much they pay.
That's how much we pay for annotators.
That's how much they pay for someone.
Per question, per annotation. Of course, as I said, we want to have several people ranking the same song pairs in order to get the best, in order to make sure that in order to minimize the noise that we have and get them as close to the ground truth as possible.
How do you know they are not randomly clicking the...
As I said, how I know they're not randomly clicking the items is that I'm checking that they're listening to the songs and then clicking the instruments that were in the song. If the songs were not, if there is a mismatch between the songs and the instruments, I know that the annotation is irrelevant, and so I can simply avoid it. I only take the annotations that were listened, click the right instrument, and so I know that at least they listen to the songs, and then I know that the annotation, if not perfect, it's at least as close as I will get to it. Demo. This dashboard platform was used for artists which we used for them. This dashboard has several features that we have thought would be useful for them. One of them would be an offline file, which would be sort of a demo. If I would present each of these models now into production, and I want to know for a specific song ID, what would be the recommendation for each, which recommendation would each model give to me? Of course, according to the data, we might want to perhaps change the similarity distance or change the number of items that we see, but the dashboard is online and live, and so it is very simple for them to evaluate and to assess how good each model presents to us or not. The other tab that we have, let's see if it works, yes, is to get a more detailed explanation for each song, what the scoring is that we found as the ground truth. The ground truth can be changed according to which annotators we are using. We can use several annotators, we can pay users, we can use Mechanical Turk, doesn't matter. Some of them were the media team that we got from artists that happily joined that someone was going to help them with the similarity search. And each model then we can then get the result for each model and how much they are different, compared to the other models. And get a more detailed information per genre. This detailed analysis per genre is of course important. 1 second. In the more overview scale, where you can, 1 second. Yeah. Where you can then go across each genre that we have and see how each model scores in that genre according to the sample that they have. Now, the main added value of such a thing is, of course, that some models perform better at some genres, while they perform less well in other genres. This allows us to do two things. One, go deeper, understand where the model failed, where model should improve, or what it is, or perhaps what it is that the model learned here well and failed to learn here. Is the problem with our feature selection? Is it the problem with our feature engineering? Or perhaps simply we have made two different models that each of them is good for one part of the catalog, but not as good for another part of the catalog. This can then allow us to decide either to improve the models in order to find one model that will classify both classify best both genres, or decide for deployment reasons to deploy this model for cinematic genres, whereas to deploy the orange model for the funk genres. Of course, since we know that such annotation is, of course, something that will continually be added as the catalog changes, we want to add them more and more. We also allow them to upload their annotations online and immediately dive deep into them and understand where the problem is and see which model fails or fares better in each one of the song pairings that we have. Let's do some things up. The problem with the data is, of course, that the data is something that changes constantly, and the data cannot be assumed to be static. We do not have label data. Similarity is not something that can be easily assessed. And even if it would be assessed, it's something that's constantly changing if we want to talk about ranking, because ranking, as the catalog changes, again, need to be reevaluated. Once we go to regression problem, the data becomes static, because even if new data is found and more similar items are found or less similar items are found, the similarity score is something that is given and will not change. One item is such and such point score relevant to another song. And this allows us to evaluate different models in future points, because it is irrelevant if the newer model have trained on greater data sets and found newer songs. As long as the previous songs are still there, the scoring allows us to compare these two songs and allows us to compare between the models and how they scored for each two songs that were found. The dashboard allows us both to developers and annotators and other teams in the department and Artlist to decide which model is the best, which model can be improved or why improved, to get a small preview of how the models will deploy in real life, and allows them to label future data whenever they want to. Thank you, and any questions? Yes?
What's the main difference between what you're doing here and a similarity with films and stuff like that Netflix is doing?
I don't know what Netflix is doing, nobody knows.
They have like some kind of a model that you take like recommendation system and then you find like films which are similar in some sense and
Netflix, as I know, are more dependent on online testing. They have developed their own in-house online testing dashboard where they're running, I think, at any time, any user is undergoing 50 different experiments, from which art they're using from the movie to whatever. By the way, that's why the reason when each time you go to Netflix, you mostly see different things and you see that the art changes constantly. It means that you were at some point one of the testers.
Okay.
So
like the main thing is like the theoretical model.
They are depending more on user experience and less on the theoretical model.
Okay, and your model is basically linear.
It's more linear, but on the other hand, it's more static. It doesn't change all the time. It takes less effort, and again, Netflix can allow itself because it has that amount of money and that amount of resources. At least it does not have those resources.
So basically, you're saying that since you're doing it offline, you can use a linear model and achieve good results.
Yes.
Okay.
So you maintain like a different one model per genre, right? Of some a different one for each genre?
No, there are several models that are running all the time, but as you see, some models fare better at some genres and compared to the same model, and you see that some genres in another genre, it would be the opposite. Okay. We can have several models, currently only shown 2, but we can have 5, 10, 15 models at one in parallel, and we can decide which one we want to deploy for each song genre.
But you can do the clustering for genres by the distance metrics.
By the way, of course, I'm talking...
For clustering would make more sense.
And how do you maintain this complexity of following by using this dashboard, like manually?
Again, we sum, as I've shown, you can see the evaluation, then you can sum by genre the scoring for each model, and then you can assess, okay, for genre 1, 2, 3, 4, I don't know, funk, pop, and whatever, model A is better. For genres cinematic and dramatic, model C is better, and for metal, model D is better.
And so you're constantly like changing which model runs on what manually and maintaining?
The model goes across the entire database. And as the database increases, sometimes the model changes or the performance of the model changes as more songs are added. Of course, some models could be decided. Of course, it allows us to know, okay, some models prefer better at some genres. Maybe we want to go later again to the model and try to improve the model so it will be better for more genres. Of course, genres is only a demonstration. This can be used for anything you want to do it for movies. It doesn't have to be genres. It can be any tag that you want to, only as long as it groups all your database in some meaningful way. If you want to do it by BPM or something like that, it works the same.
Thank you.
Other questions?
Yes.
I was wondering about the instruments. You said you were just using them as a method to verify the
Yes.
mechanical terms are actually doing their job. I wonder if they had any intrinsic value in the similarity.
For this thing, they did not have an intrinsic value. Of course, some of the models do use the instruments as features, but these features are assessed by the model, not by the annotator. Other questions? Thank you.